Welcome to our presentation of the paper titled DPGEM Differentially Private Generative Model with Exponential Mechanism. Introduction. Privacy preserving distributed machine learning allows collaborative learning while protecting sensitive data. The methods commonly used are federated learning, homomorphic encryption, and differentially private model training. Synthetic data can be used in place of real data without any impact on downstream learning tasks. Synthetic data allows human in the loop operations such as expert labeling. Differential privacy can be combined with generative models such as generative adversarial network or GAN as the means to integrate privacy with synthetic data. However, techniques like differentially private stochastic gradient descent or DPSCD method face two main challenges. The first challenge is of convergence because of noisy training of models. The second is difficulty scaling to high dimensional data. An alternative approach trains a generative model such as a GAN on publicly available data and then models its latent space to identify private vectors. Differentially private synthetic data can then be generated in two ways. The first one is to train a differentially private GAN on these public and private latent vectors, and the second method is to employ the exponential mechanism in differential privacy to sample private vectors from the latent space. However, when sampling assisted exponential mechanism is employed, two main challenges arise. The first one is that the sampling process may struggle to reach the high quality private regions in the latent space. The second challenge is that the privacy budget needs tighter analysis such that a large number of synthetic samples can be released. Differential privacy. We consider the basic definition of differential privacy. We say that a mechanism or an algorithm M applied on a private database X is epsilon differentially private uh, if the following guarantee is provided for any outcome S. So this guarantee basically means that the odds of database X and any of its neighbors X prime producing the same output S are not very far. They are bounded by this parameter epsilon. The parameter epsilon is called the privacy budget. The smaller the epsilon, the stronger is privacy. An important property of differential privacy is composition, which implies that if the same query is answered by a private mechanism multiple times, then the privacy degrades. However, the degradation is graceful. Exponential mechanism for differentially private generative models. The exponential mechanism can be applied at the output stage of a generative model to get differentially private synthetic samples without disturbing its training process. It releases a sample B with the probability that is proportional to its utility value uh, obfuscated by the privacy parameter epsilon and then exponentiated. The utility u of b can be provided by a discriminative classifier that favors private data over public data. The term in the denominator delta u is called global sensitivity. It is the maximum possible change that can happen in the utility value b over all the neighboring data sets x prime and over any possible output b. The privacy loss incurred by answering a single query b is proportional to this term, where in the denominator we have the global sensitivity. In the numerator, we have this term u super s of b, which is called the utility spread. This is the maximum change in the utility value that can happen only for the sample of interest b, instead of considering all the samples possible. Here are the key contributions of our paper. First, DPGEM utilizes an improved scoring function By utilizing a classifier that is trained on the synthetic representations of sensitive and public data. Second, the DPGEM implements a per output element local privacy composition method to obtain tighter privacy bound and hence release more samples. Third, we present a method for fast privacy accounting that is based on uncertainty measure used in active learning. Our method identifies high impact data points for fast accounting of privacy budget. Model inversion of public generator. To obtain synthetic representations of both public and private data as given by the public generator, we employ this model inversion process. We begin by feeding a random noise vector to the generator that is already trained on public data and its weights are frozen. Then we define a loss function on the generated sample and on the real sample whose representation we want. We update the vector in the latent space to minimize the loss function. Um, and then these vectors map to the synthetic representations resembling the real samples. We optimize the loss function such that the search is close to the standard Gaussian. This model inversion process in this manner is able to search the latent vectors that map to the private data. Training synthetic data classifier. This is how we train the synthetic classifier on the synthetic representations we obtained, such that it will serve as the classifier will serve as the utility function for the exponential mechanism. We perform the model inversion process on the real data and obtain public and private vectors. We map them back to get public and private representations. On these representations, we train the classifier or the scorer dx. So the classifier gets this ability to distinguish private latent vectors from the public ones. And our DPGEM framework uses this classifier to search for more private regions corresponding to synthetic corresponding to the private data in the latent space. This is our main framework, exponential mechanism for private data generation. We utilize the classifier dx to serve as the utility function ux. We feed a single random vector to the exponential mechanism, which then employs the Hamiltonian Monte Carlo or HMC sampling method to search for the private vectors in the latent space of the previously trained public generator. These vectors are converted into samples by the generator, and then the utility scores are provided by the classifier. The HMC sampler is guided by the scorer to navigate through the latent space for private looking vectors. The generator continues to release the differentially private samples as long as the privacy accountant allows it.